Hello, class. Today we explore momentum, a fundamental concept in mechanics. Momentum explains everything from vehicle safety to rocket science. Whether we are trying to reduce the devastating forces in a car crash or maximize the thrust needed for a rocket to leave Earth, understanding momentum is key. Let's begin by formally defining momentum. What is momentum? Mathematically, it is the product of an object's mass and its velocity. Think of it as a measure of an object's motion. The more momentum an object has, the harder it is to stop. Note the units, kilogram meters per second. Momentum is a vector. This means direction matters just as much as magnitude. For example, a heavy hammer moving fast has significantly more momentum and is much more difficult to stop than a fast-pitched baseball. Next, let's look at how momentum is central to Newton's second law. While you may know F equals ma, Newton originally defined his second law in terms of momentum. He stated that the resultant force applied to a body is directly proportional to the rate of change of momentum. This perspective is vital when mass is changing, or when calculating the force required to bring a moving object to rest. In the lab, we can use a data logger to record a trolley's movement. If we plot a graph of momentum against time, the gradient of that line tells us the accelerating force. A constant force results in a constant rate of momentum change. One of the most powerful laws in physics is the principle of conservation of linear momentum. It states that in a closed system with no external forces, the total momentum before a collision is equal to the total momentum after. We see this perfectly in a Newton's cradle, where momentum is transferred from one ball to the next, proving total momentum is conserved. The law of conservation of momentum applies to both collisions and explosions. In many collisions, objects join together, or, quote, coalesce. If a defender tackles a stationary player, we add their masses together to find their final velocity. By conserving momentum, we find they both move with a shared velocity. In physics, an explosion occurs when a stationary object separates into parts. Since the initial momentum was zero, the total final momentum must also be zero. This means the pieces move in opposite directions. For example, when a boy steps forward out of a boat, the boat must move backward with an equal and opposite momentum to keep the total at zero. Finally, let's explore how momentum connects to Newton's third law. Conservation of momentum is the reason behind Newton's third law. For every force, there is an equal and opposite reaction. When the Earth pulls an apple down, the apple pulls the Earth up. Because the Earth is so massive, its change in momentum results in an unnoticeable change in velocity. But the principle remains absolute. Let's quickly summarize the key takeaways for your exams. To succeed in your exams, always remember the core formulas. Momentum equals mass times velocity, and force is the rate of change of momentum. Use the momentum before equals momentum after rule for every collision and explosion. Always remember, momentum is a vector. Direction is crucial. Master your vector resolution using sine and cosine, and you'll be ready for any mechanics challenge. Keep practicing.